Right, our discussion today is a very interesting one. It is a discussion that focuses on the most popular area on what you call numerical methods and we're focusing on some revision discussion here. And now we are going to start by looking at the finite difference method. We need to set up the system of equations to solve the boundary value problem, right, which is y double primed by x plus y primed by y. And this is the past exam question that came in November last year, exactly as it is. Minus y squared equals to x. X lies in the interval from 0 to 2, and you have the product here of y primed of 0 by y of 0 equals 1, and you have that y primed of 2 is 0. But by the method of finite differences with the change in x equals 1, here we advise not to solve the equation. So we're not going to solve the equation, or we're not actually going to solve what we call the equations. Right, you're not going to solve the equations. Okay, right, so we proceed to solve this particular problem, but we will solve this particular problem in a step-by-step fashion as follows. Right, in looking at the solution, there are a couple of things that we need to sort of remember. So to solve this problem using the method of finite differences, or the finite difference method, is we let xi. Right, we let xi denote. Right, we let it denote what we call the grid points. Right, the grid points. Right, with h equal to xi plus 1 minus xi. And let YR denote the approximate. The approximate value y evaluated at xi. Right, so we let x sub I denote the grid points with h equal to the x sub I plus 1 minus xi, and we let the yi denote the approximate value here, y of xi, like so. We will use the following. The following approximations. What are the approximations? Right, the approximation we're going to use is that the second derivative, the second partial derivative, right, of y with respect to x squared, evaluated at x equals xi, is approximately yi plus 1 minus 2yi plus yi minus 1. And you divide by the square of h. Right, you note therefore that this is exactly the approximation of the second derivative, the second partial derivative, And now the d squared y dx squared evaluated at x equal to xi is approximately y sub I plus 1 minus 2 y sub I plus y sub I minus 1 divided by the square of h. Okay, we can divide by the square of h, but also we can um, use delta x or delta t, like in the question there in the place of the h, but also in using the method of finite differences to solve the exam question, we navigate and we realize that y itself, if we happen to evaluate it at an xi, it is approximately, okay, these are approximations, it is most certainly approximately yi, like this. Okay, so with these then, we must mention, and of course, we note that x itself evaluated at x equals xi is actually x sub I, like so. Thus, the differential, right? Thus, the differential equation can be approximated. Can be approximated at a grid point. Right, can be evaluated at a grid point x sub I by the, so now we want to approximate the differential equation that has been given to us in this question. So we can be able to take the differential equation and we can approximate it at a grid point x sub I by the difference equation. Right. So the difference equation is sort of the ultimate here because we understand that it is the ultimate thing we actually achieve because it's what we use to find the equations they want. Right, so to solve this, we will obviously note a couple of things. Right, I'll first write the past exam question, this one, plus y primed y minus y squared, and this is twice x, and it is x in the interval 0 to 2. And obviously, this is done with the initial values, two of them, which is 0, y 0 is 1, and this is 0. Okay. Right, so what would therefore the difference equation become here? We need to think about this. So it will therefore become, for the second derivative, it's just going to become y I plus 1 minus 2 yi divided by h squared, which is now exactly now this is the y double primed. And then now there's this x, which you can just call xi. And then plus. And then you come to the y primed. So this y primed also is like a small one. So you can use any of the relations we have. But also you can consider the fact that this one here is can be seen as can use any of these relations. Okay, so I'm going to write just one suggestive relation here. Yeah, it's twice. So normally we use here yi plus 1 minus yi minus 1 for this y primed. That is the sort of the difference equation we use. And it is always divided by twice h. So, okay, we are realizing that the double prime is written like this. The difference equation for the second derivative and for the first derivative is written like this. And this is exactly standard. These are exactly standard symbols used in the course. And then now you have the y, which is exactly yi. And then this is exactly minus yi squared, which is 2xi. Like so. Like so. Now, once we write this, then, and now we need to remember something that has been given here in this question. The examiner gave us that delta x is 1. So h is 1 here. Right, so this is true, but it is true with h equals delta x equals 1, like this. So we continue. We continue now to manipulate this. So once we know that h is 1, so we substitute everywhere. And then we get the answer. So if we substitute everywhere, what are we going to achieve? For example, substituting here will give y sub I plus 1 minus 2yi plus yi minus 1 into xi. Okay, this is already 1. So we continue. Right, so we continue here. Now we replace h by 1. So, and this gives us yi plus 1 minus yi minus 1. And this is exactly which is exactly yi. All right, now with that said, then we continue and we say that this is minus yi squared, and this is 2xi. Okay, and this is exactly what we are able to achieve here. Right, continuing with this, now we are solving this problem of October, November 2023. So we are in business and we're analyzing this. What do we then do at this point? Right. What we then do at this point is to bring about further analysis of this. So we note, therefore, that we have y sub I plus 1 minus 2yi plus yi minus 1 into x sub I plus yi plus 1 minus yi minus 1 y sub I minus y sub I squared, which equals 2xi, like this. So now we continue. We continue. In continuing, there are a couple of things that we shall analyze on the way as we move along. Right, so we note that the grid, right, so the grid in this problem consists of the following points. Right, so okay, so we continue. We continue. We continue. Right. What else do we then have at this point? Right, a grid in this problem consists of the following points. Right, consists of the following points. Because of the initial value that we have between 0 and 2, so which means, but also you have that there is in the a y0, which goes with an x0, and the x0 is 0. So it means that you shall have that the x0 equals 0. And then you continue to add the h until you reach the 2. So because the x's are between 0 and 2. So if you add now, you get you add a 1, and then you add again x2. 1 plus 1 is exactly 2, like so. And what is the meaning of these? So now, with these, we're able to further analyze these in some detail and see what next is to be done. Let's call this one equation star. So equation star needs to be applied at all grid points at which the value of the function y is actually unknown, is unknown. Right. So we're saying equation star needs to be applied at all grid points. So we're going to apply this at all the grid points at which the value of the function y is unknown. Obviously, we are dealing with many points where the value of the function is unknown. This usually includes, right, these usually includes all grid points in the interior of the region but whether the values of y at the boundaries of the region are known, or not. Whether they are known or not, actually, it depends on the boundary conditions. Right, it depends on the boundary conditions. Okay, depends on the boundary conditions. Okay, this usually includes all grid points in the interior of the region. So once again, all grid points in the interior of the region, but whether the values of y at the boundaries of the region are known or not depends on the boundary conditions. So obviously, that is pretty obvious. It depends on the boundary conditions because it depends on what the boundary conditions are able to assert in terms of what is known and what is not known. Okay, so we look at this question, but we look at this question with a very, very careful eye, and we analyze this in great detail, and we look at what happens here. We look at what happens here. All right. Now, the boundary conditions in our case, this problem, the boundary conditions are, so you just copy them down. Right, the boundary conditions are these. So they are y primed of 0 by y0 is 1, and y primed of 2 equals 0. So you write them down. Right, the boundary conditions are y primed at 0 by y at 0 equals 1, y primed at 2 equals 0. Like so. And what is the meaning of this in this case? So what would y0 be? And what would, okay. I want us to analyze these together. Y0, y primed of 0, y0 is 1, y primed at 2 is 0. Now, this has, this one can be seen as, like the the y of 0 can be seen as y0. So the top, this one implies, this one is like y0. And this one is y0 primed. And then this one, now you need to, because we're looking at y0, y1, y2, y3, and so on. What is the position of this y value in relation to, because now there is y0, there is y1, and then this one is going to be y2, because delta x is 1, which is the h. So if we start with x0 here, which is 0, x1 when you add h, and then x2 is just going to be 2. Oh, because we're adding the h, 1 plus 1 is 2. So, and this would mean, therefore, here, this one is like y2 primed is 0. Like so. Right. And so what then do we do here? What then can we achieve out of this here? Okay. We obviously need to analyze this carefully. And here you need to realize that y0 are not known. Y0 explicitly is not known, but we know the product is 1 of these two. But also here we know that y2 primed is 0. But that does not mean that we do not know exactly y2, for example. Right, so what do we do now? Right. Now, let me write something here. Now, y2 primed is 0. But why not? Is not known. Is not known. And therefore, okay, I can write that. Let me write more. Okay, I can just add something here for completeness of this. Right, can just say, okay, the y primed, okay, need to get my power. Just 1 sec. I forgot to do with heavy lightning and thunder, so I disconnected the power, but now I'm forgetting that um the lightning is gone, so I can get the power connected. It right, system connected. Okay, right. So we're right back. Now I was saying that okay, we can see that y2 primed is equal to 0. But also we can see that y0 primed like this is 1. Now this is the case. Okay. And therefore, right, and therefore we need to apply star at x naught. Okay, we got that equation star at x naught as well as at the interior. Right, at the interior grid points. Right, and the interior grid points are, because now we have already got these x values, x0, we start from it, and then we have x1, x2. What would the interior points be, for example, here? Okay, remember that, so that's not really a big problem. The interior point is going to be x1, which is 1. Okay, because these are like exterior x0 and x2. This is like interior, looking at the interval 0 to 2, like this. Okay, we continue. Now, since, right, since the equation star refers to the value of y okay, it refers to the value of y sub I minus 1 that we've seen at a grid point. Okay, we're gonna write down, we're trying to just discuss, and then we shall write down the equations they want at a grid point. Okay, right. Yeah, at a grid point xi minus 1. This one refers to the value of this at xi minus 1 to the left. To the left of the current grid point. Grid point. Right. The grid point being xi. To be able to write, to be able to apply star at the grid point x naught, we need to also include the value for y at x minus 1. So at x minus 1, because now we are dealing with the steps, so this one is going to be like minus 1. Which is outside. Okay, because we're looking at what happens when I is 0. So you have x sub minus 1. So one step, because h is 1, so one step back is minus 1. But this minus 1 now, because we're looking at between 0 and 2, and this minus 1 is outside, which is outside. Which is outside the domain. Outside the domain of the differential equation. Of the differential equation. Okay, the domain is between 0 and 2. According to the question, we saw that. Now the question becomes, how do you handle this problem? To handle this problem, we will introduce something we call a fictitious point. So introduce a fictitious point. Right, what fictitious point? Like at yi minus 1, this is at xi minus 1. For x sub minus 1, we consider the corresponding y to represent the value y evaluated at minus 1. We will write out the set of equations. The set of equations using these extra point. And then use the derivative. Right, the derivative Right, something called the derivative boundary. The derivative boundary value to eliminate it. Now we continue to analyze this past exam question as follows. The application right, the application of star at x0, x1, x2 gives, okay, you can put an and here, because if you're writing a list, you can say x0, x1, and x2, because these are the only things. X0 is 0, x1 is 1, x2 is 2. The domain is between 0 and 2, so these will be the only ones because we're guided by the step size, which is 1 this past exam. So gives the set of equations. Right, so what are the equations that we... Okay, the best is to first cite the equation star. Let's just bring it back. Right, here's the equation star. So we'll take this equation star right. So we're just going to write it now, and the equation star is yi plus 1 minus 2 yi plus yi minus 1 xi yi plus 1 yi minus 1 yi squared xi. So we continue. Right, so obviously, I mean, the couple of things that are very, very essential here that we will take into account. And now the application of star at these points at x0, x1, x2 gives a set of equations. What are the equations and how many will they be? So we analyze this because now the x's themselves are 3 of them. And so because they are 3 of them, we actually expect the number of equations to be the same, 3. Okay, so let us write those out. Now, if we put x I equal to 0, what do we have I equal to 0? So we would have y1 minus 2y0 plus y minus 1, and then x0 plus y1, y minus 1, y0, y0 squared, 2x0. So now this one is at the point where we don't need to solve this, but we need to find these equations. But now this is where I is 0. Okay, and then the next thing is we shall get this when I equals 1. When I is 1, we shall get y2 here, 2y1, 0, because we're making I equal to 1 now, x1, y2, y0, y1, y1 squared, 2x1. Now, then we continue. This is when I equals 1. And then we can continue and look at what happens when I is equal to 2, for example. How does it affect the x's? Does it yield any of them? Okay, because this up to x2, so it makes sense. We can take I equal to 2. And when I equals 2, then we get another equation, which is y3 when I equals 2. And then you have 2, y2, y1, x2, y3, y1, when I is 2, y2, y2 squared, 2x2. Okay, so this is what we're getting. And these are all of them because they include now x0, x1, x2. Okay, so these are all the equations. And then after these, we ask ourselves the question in terms of what else can we do here? Because we already know the x0, but what is x0? But, however, we have knowledge of the fact that x0 is 0, and then we add 1, and then we add another 1, we get 2. So we can just substitute these things. And then if we substitute those things, then leaving us with only the y's, then we have something nicer and simpler. So which means that at this point here now, we're gonna just have this equations, and then we're gonna perform substitutions. What substitutions? The substitutions of the x0, x1, x2 into this. So which means that you're gonna have the following: y1 minus 2y0 plus this one, the x0 is 0, plus y1 minus y sub minus 1, y0 minus y0 squared is equal to 2x0, which is 0. Next, we have y2, 2y1 plus y0. X1 is 1 plus y2 minus y0, y1 minus y1 squared is 2x1, which is 1. Then we have y3, 2y2 plus y1. And then there's an x2, okay, because we're just substituting into this, the x0, the x1, x2, x0, x1, x2, just substituting the x's, and then we're going to be left with the y's. So here we're putting now x2. X2 is 2 plus y3 minus y1. And then we have y2 minus y2 squared. And x2 is what? Is 2. Like so. Now let us simplify this and see, for example, 0 by this is going to be 0. And this is going to leave us with this here, this one by that. So it's going to leave us with y1 minus y sub minus 1, 0, y0 squared equals 0. This one, it's everything like that. Okay. So interesting. Okay, this one, 2 by 1 is just going to be 2. So we're just left with this. And then, yeah. And then here, you can write y2 minus 2y1 plus y naught plus y2 y naught y1 y1 squared equals 2. And then here, you have this y3. y3 2y2 plus y1 times 2 plus y3 minus y1 y2 okay, minus y2 squared equals 4. Okay, can write it like this. And then we watch this and check any further simplifications that are possible, but also using the boundary values, the initial values. Right, so now we have this, like this is y2, y1. And then this is y0, y1 when you multiply. Y3, y2, and so on. Right, so with this said, with this mentioned, we look at this and think very carefully. But most importantly, the next step would have to be to apply, and that is what we are doing. Next, we apply the boundary conditions. Right, so we will remember the boundary conditions. Okay. Y of 0 primed. Y0 is 1. Y primed 2, 0. Okay. So now we'd remember that we have already said here that the Y primed is actually the same as yi plus 1 minus yi minus 1 divided by 2h, like this. Now we're going to use it here. Right, so when you use it here now, what would that mean? For example, for this one, what is the meaning of this? But also, if we're interested in finding y primed at 2, what would the values be? For instance, at I plus 1, at I minus 1, relative to 2, what will that be? So we analyze that part there. So now this means at this point here, we can start here and realize that this is going to be y1 at 0, at 0, at x0 equals, at x0, which is indeed 0. And at x0, we have I equals 0. Right, so when I equals 0, therefore this one becomes a y1. And then this one becomes minus y minus 1 out of 2h, but h is 1 for this problem, multiplied by. So here now you'd have only y0, y of x0, y at 0. So this one is like y0, which is 1. And then now we come to this one. So this one here is something very similar, but it is quite interesting. It is quite interesting in its own right because it has its own specific attributes. And we actually look at that part. We look at that part exactly. And I want to give a comment on that one. So, which means, now this one here is, we have seen that it is the same as y2 primed, which equals 0. The same as y2 primed, which equals is 0. Right, and obviously we look at this and we substitute here h equal to 1, which is delta x in this problem. So this one is going to be exactly y1 minus this. And then you have y0 and y2 like this. We can distribute and look at similarities here. Is there any y1 minus, let me see, y1 minus y sub minus 1, y0 is 1. So that is what is going to be used to replace some of the things. Like here is going to be replaced, is going to replace this one, and it's going to make this one a 1, so that this is going to give us y0 squared. And then now we're going to have also, so we're going to use these particular boundary conditions. Okay, let's analyze those with much caution and make sure that we get the most out of these together. Okay, so we most certainly are able to note that. We're able to note exactly that. Right, so there are a couple of notes we need to make as well. we have seen that to find the y primed, we evaluated it at the x0, and at x0 we looked at the fact that I is 0, and then we put here I equal to 0, and then we got 1 minus 1. But here I at 2, I is 2. Here I is 2, because this one is like computes the y primed at x2, right? Which is y primed at x2, which is 2, and which is 0. Okay, that is telling us something about the I here, that I is 2, and then we can be able to compute y1 minus y minus 1, okay, subscript right. So we have this one is y0, 1. Now, when you come here at I equals 2, at I equals 2, what do we get? So you're going to get y3 minus y1 out of 2 into 1, because h is 1. And therefore, this one here is equal to 0. Right, so what are we getting here? y1 minus y sub y0 equals 1. And then here, this one is y3 minus y1 equals cross multiply 0. So y3 minus y1. So is y3 minus y1 is 0. Obviously, I mean, we're getting a couple of things here. For example, this particular boundary condition tells us that y1 equals y3. And this one is y1 minus this. And then is y0 equals 1. Okay, let's check. The usefulness of this here, some of the things. Like we're getting, this one is 1, all these. So, which means therefore we're going to substitute this by 1, and then we shall be able to get the y0. And then now, anything else? y3 minus y1, is it y3 minus y1 this? y3 minus y1 is 0, which is going to further simplify some of these equations. So let's just carry this forward. Let's just carry this forward. Okay, we continue. Yeah, just carrying the last equations, because we're just going to substitute the things we know and then look at the simplified equations, because in the end we need to, okay, we know we're advised not to solve these, but we need to leave it at a state that is simplified, and we've substituted the known things, etc. So, right, we note that exactly. We note that precisely. Right, so we write this one. Y which is 0. Two y1 plus y0. Minus y0. Minus 2y2. And then 2 here. Plus y3. Minus y1. Y2. Minus y2 squared equals 4. Okay, now let's look at this and realize, what is y3, y1? It's 0. What is y, according to the given boundary conditions, this is going to be that. So we have implications that this one, for example, is going to just become 1 minus y0 squared equals 0. Right. This one, the y3 minus y1 equal to 0. So this one is going to just become 0 everything. But also, this one means that y0 squared is 1. So we have some benefits from that wherever you see y0 squared. But also here, this one being 0, it would imply for the bottommost equation for y3 minus y1. So, but this one is y3 plus y1. What is y3 plus y1? So this one means that you have y3 minus y1 plus 2y1 equals 2y1. And this means that y3 plus y1 is 2y1. y3 plus y1 is what? Is 2y1. 3 plus y1 is 2y1. So this is going to be 2y1. For y3 plus y1 minus 2y2. 2. y3 minus y1 is 0. 0. This one. 0 y2 minus y2 squared equals 4. So this is what this equation becomes. And then we just have this one in the middle. Anything that we can sort of be able to replace here? Not so immediate, but we have exactly this. So it means that we have the following. Right, for the topmost equation, we have y squared equals 1. y0 squared equals 1 for this one. And then for the second one, we have exactly these. So which means that we have the y2 very interesting this. Right. It's very interesting that we have just a square term here. Yeah, because of this, because of the y squared. Okay, we have a square term. Right, so normally these are quite linear, but yeah, that's what we have. So, right, so we have therefore that the y0 squared is 1. And then we write the second equation, y2 minus 2y1 plus y0 plus y2 minus y0 into y1 minus y1 squared equals 2. The bottommost equation is this one. Obviously, now this is 0, and so you'd have only the, you can write it like this, or many ways. You can write it as 2y1 minus 2y2, but you can factor out the 2 because the common factor, making it y1 minus y2 with a 4 outside. Y1 minus y2 with a 4 outside. Then this is 0 minus y2 squared. Like so. Okay. This system, you can call it double asterisk. So it is something that we've got. And we have these equations. Right, and therefore these equations are the answer to the problem. We don't need to solve this. We just need to find them, and we have found them. So obviously one can always look at how to solve them, but you're not asked to solve them, so we're good. Okay, so we've solved this question. So what was the question? Quickly, and then move to the next one. Right, so the question was set up the system of equations to solve the boundary value problem by method of finite differences with delta x equal to 1. Do not solve the equations. Please, the equations are not supposed to be solved for this one. Okay, and we're done. Right, the next thing now, we're going to look at the shooting method. The shooting method question was brought also as part of the 2023 November exam. So let's look at the shooting method. Okay, right, let's look at the shooting method. November 2023, here's the question. Okay, it was given just as part of the question 3, because we're just doing, question 2. So we are working on question 2 of November 2023. And the question is actually part B. And we're saying consider the boundary value problem y double primed, which equals y plus x. Y at 1 is 1. And then y at 3 is exactly 2. The instruction is you need to solve, or the question is you need to solve this system over the interval, right, over the interval, x lies between 1 and 3, by using the shooting method. right, so the shooting method always goes with the approximation method that is going to be used, because this is about guesswork, the shooting method. So you always start with the guess and then you work towards the desired value. In this case, we are starting from y1 equals 1 to y3 equals 2. So you need to use the Euler method. So it always goes with Euler or the Runge-Kutta of order 2, etc., etc. Any of those approximation methods. Right. With delta x equal to 1. So, okay, solution. Right. Now, a couple of things are important. Consider the boundary value problem this. Y1 equals 1 and y3 equals 2. Solve this system over the interval x lies between 1 and 3 by using the shooting method. Use the Euler method with delta x equals 1, or just the h equals 1. Okay. So let us look at this problem and solve it together. Very interesting, nice little problem that came in November. Now to solve this, we go to the basics of the shooting method. And we look at what makes up the shooting method. The solution to this problem. All right, to solve this, we note that the boundary value problem is y double primed. Okay, is y double primed, which is equal to y plus x. Y at 1 is 1 and y at 3 is 2. What are we supposed to do to solve this problem using the shooting method? First, because it's second order, we must reduce to first order, because the Euler method works for first order. So we must convert it to first order. How do we convert to first order? We use substitution. We must convert the second order. Right, we must convert the second order differential equation into a system of two first order equations by introducing a new variable. Right, introducing a new variable. The variable is z equals y primed. This gives us the system. gives us the system. All right, so if you have the y double primed is y plus x, and then y at 1 is 1, and y at 3 equals 2. So this is similar to the following. Okay. So we want to remove this second order and make it first order, this. So how do you do that? We take one of the y primes and we call it z. So z is y primed. Y primed. So we have here that y primed is equal to z. That is a substitution. Because there's a y primed and there's another primed. So in other words, it's y primed, which is y double primed. So we take that and we break it down into the thing, into the first order. All right. So now here we're going to have this. But now if here, therefore, we call this y primed z, it means therefore you're going to have z primed. Z primed, which equals y plus x, which is y at 1, which is 1, and then y at 3, which equals 2. Okay. Because that's what we have for y. But now for z, what are we going to have? Okay. So for the y prime equals z, we have y at 1 equals 1, y at 3 equals 2. So would be interested in knowing a couple of things now. Would be interested in knowing z at 1. What is z at 1 here? Okay, we think about this. And let's write something small. I made this comment, but the reason for this conversion is that the Euler method is a method for solving first order differential equations right, first order differential equations or systems of first order differential equations. Okay. It can be used, or rather it can't. So it cannot. It cannot be used directly to solve a second order. A second order differential equation. Okay. Right, with this said, then we are at liberty to continue and solve this problem using what we call the shooting method. Once again, it relies on the use of other approximation methods there, but we must just start with an initial, with the slope, and we shall see what that means beginning with the slope. So we start with the gas. We start with the gas. To apply the Euler method, we need, okay, we need the value of z at 1. Because we have y at 1, we need z at 1. Okay? We need the value of z at 1, which is, but we don't have it. So always it's not there, but we need to guess it. Since the value is not known, we will make a gas at its value. At its value, and see how close the obtained y3 value is to the required, yeah, right, the value is to the required value. Now the required value is called d. Okay, so it cannot be used directly. Once again, there to the Euler method cannot be used directly to solve a second order differential equation. To apply the Euler method, we need the value of z at 1. Since the value is not known, we will make a guess at its value. We'll make a guess at its value and see how close the obtained y at 3 value is to the required value d equals 2. Okay, and the d equals 2 is this one, d equals 2. So we need to get this. But now the question is, what value of z do we z of 1 do we start with? There's y at 1, but the z at 1, we guess that one. All right, so we start as follows. So let us guess. Let us take let us take as the first guess is the first guess. Okay, we call it guess 1. We suppose that this guess 1 is 0. We start at 0. And solve. And solve the system. 1. Okay. This one. Let's call it 1, this system. Right, this the system 1 with with z at 1 equals guess 1, which equals 0. Okay, the guess 1 is a z at 1. So the calculations are what is y at 1? Okay, y at 1 is 1. Y at 1 is 1. And then if this is the case, what is z at 1? Z at 1 is 0 because we just guessed. Let's start with 0 because we want to move towards 2. Want to move towards 2. So we said let's start at 0 and then we'll possibly get to 2, the ultimate. So we just a guess. It's not quite justified. So we continue. So now we will use the Euler. What is the Euler? Okay, we did that many times. Predictor, yi plus 1, yi plus h, if xi, yi. Okay, this is the predictor. Euler, not the modified Euler, it is a corrector and a couple of corrections. So with this, then we shall be able to get like y at 2, because we have y1. Y at 2, remember the h is the h here is 1. So just add 1 to get y at 2. Okay. Y2. And then now if this is y2, then when I is 1, so this is going to be y1. Okay. H f of x1, y1, which means y2. What is y1? It's 1 plus h is 1. F is the differential equation. What is this now? Okay. So this one is the y primed, but we know that y primed is z. Y primed is z. So y primed is z. So that now we're going to have here z1. We're going to have z1. Why we have 1 here plus 1. Z1 is 0 here. And the answer is 1. So you have y2 is 1. Then we then can get, because we start with y, z. So y2, z2. Z2 now. Z2 equals Z1. Yeah. Z2 is Z1 plus H. And then you're gonna look at the derivative of the Z. Because if this is Y, then it becomes the derivative of the Y, which is the slope. So what is Z primed? Z primed is y plus x, the slope of z. According to Euler, you must always put the slope. So is y plus x. So you can put here y plus x. Okay, so what is z1? 0. H is 1. Y1 is 1. X1 is what is x1? Right. X1 is 1 because it's y. You know, x1 is going to be just a 1. Okay, it's going to be just a 1 so that this becomes 2. Can elaborate on that, but yeah, it's going to be exactly this. So next we got the Z2, this one. And then now we need to get Y3. What is Y3? Right, so Y3, then from Y3 you can get Z3, etc. Okay, let's get Y3. By Euler, we know that, write small Euler here. Yi plus 1 is Yi plus HF Xi Yi. So write everything written to Euler in yellow. So which means now this one is Y3. Which means it is Y3. And now the Y3, according to this, is going to happen when at what I value I'm going to have 3. Okay, because you're starting at Y1, then there's Y2, and then there is y3. Okay, so let's continue now. Okay, we can analyze that in many ways. But now the y3 is going to be the same as what? According to this, it's going to be just one less. So it's going to be y2 plus the h is 1 into the slope of the y. In other words, y primed. What is y primed? It's just z. Y primed is z. So because this f xy is the slope dy dx. So which means that here we're going to have y primed. And then what is y primed here? Y primed is z. What is z at 2? It is exactly 2. So you can write here h plus zeta 2, which is like y primed. So y at 2 is the same as what? Y at 2 is exactly 1. How do we know? Because we know y at 2 is 1 here. And then h is like the delta x 1, and then z2 is 2, and then this is 3. All right, and we have this. Okay, there's a note here according to the things we found so far. We need to note that the order of calculations we need to find both y2 and z of 2 before we can calculate y3. Okay, we mentioned that we don't need to find z at 3. Okay. The value obtained for y3 was, okay, we got the value to be 3 for y3. Right now, we have a specific symbol for that. All right, we call it the R value. So R1 is 3. Because, why are we calling it like this? We're calling it R because it was a miss, because we did not get the answer we expect. Because according to this, then y3 must be 2, but we got a 3. So it's a miss. We are shooting. They call the shooting method. So we missed with the initial guess we made of guess, the guess 1 equals 0, which was at 1 equals 0. Okay, so now was R1 equals 3, which is not. Which is not equal to the required value D equals 2. The means through the shooting method is called R1. The required one is called the D value, D equals 2. Therefore, we must make another guess because that 0 did not work. The first guess 1 equals 0, G1 equals 0 did not work. So therefore, we must make another guess. Let us take guess 2 now to be -1. Not largely justified, but we take this and okay, we need like 2 guesses because if we have like we make 2 guesses and they miss, then the third one is going to be the average, and normally it actually is able to get the desired result y3 equals 2. So let's see the -1 and see where it's going to lead us. Okay, so with z1 equals now guess number 2 and it is -1. The calculations are what are the calculations? We know that y at 1 is 1 according to the given problem, but we know that z at 1 is the guess, which is -1, guess number 2. We know that y at 2 equals what? Okay, so to get y at 2, we use the Euler. So for y at 2, then it's going to first be y at 1. Euler. What is the Euler? yi plus 1 equals yi plus hf xi yi. Right, so with this said, we have the following. Yi plus 1, I know I'm just writing this, but you know it already, Euler, xi, yi. So now this is obvious. It's known very well. Is one of the approximation methods. So now we're gonna shoot, starting with the initial guess, and we're gonna see if we're gonna miss or we're gonna fire, or we're gonna misfire. Okay, so let us continue now. Y2, according to this, Y2 is gonna be Y1, H, okay, and then this is gonna be F1, that. Or what is Y1? 1. Okay, and then there's gonna be, okay, and then this fxy is the slope of y. what is y primed? Y primed of 1, of x1. Right, so let's check. Okay, that one we know very well. Y primed at 1 is a z1. So if y primed is z1, what is z1 now? -1? Right, it is exactly -1. 1 minus 1 a big note. Y2. And then there's z2. Okay, because now we get y1 z1, y1 z1, y2 z2. Okay, so this z2 is going to be z1 plus h times z primed at 1. According to Euler, is the slope, is the derivative of this. Okay, so what is z1? Is the gas. We guessed now -1. And then h is 1. And then what is z primed? Z primed is y plus x, which is going to be y1. What is y1? It's exactly a 1. So this is going to be y1 and like x1, something like that. -1 plus 1 into y1 is what? It's a 1. We saw that before. X1 is what? It's a 1. And therefore the result is 2 minus 1, 1. Next. We're going to focus on now y3. 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 Okay, so y3 is first y that is just 1 less, y2, plus h, then the slope of the y, which is like y primed at 2. Yeah? So what is y2? 0. 1. Y primed of 2. Okay, the y primed is z2. Y primed at 2 is going to be z2. And what is z2? Z2 is 1. Okay. And so what is this? It's exactly 1. So y3 is 1. But we know that y3 is 2. Because in the shooting method, we already know the answer. But we need to use the shooting method to show that we can achieve the answer through an initial guess. But once we make 2 guesses, then we can be able to get, and we use what we call the interpolation formula. So what do we say now here? We obtained a value we first made a miss of, we got a 1 for y3. We call it R2 for y3. But again, oops. But again, it is not equal to, is not equal to d equals 2. We want 2. Okay, but yeah, here we obtained the 1, which is again not equal to d equals 2. And therefore, oops, oops. And therefore, we need another gas Okay, we need another gas, but this time since we have available for us the results of 2 gases, we use the technique of interpolation to make a better gas. To make a better gas. The interpolation formula is, right, we use the interpolation formula, the G formula. So it is namely G3 minus G1 divided by D minus R1, G2 minus G1, R2 minus R1. Okay, now we have this interpolation formula where G3 is the next gas. Right, is the next gas. We therefore get let's make G3 the subject here. Okay, if we make G3 the subject, we cross multiply, and this D minus R1 is going to sit on the other side, and then it's going to be plus a G1 there. So we're going to, by manipulation, get G3 equals G1 plus G2 minus G1 divided by R2 minus R1, this minus R1. So the value of the next gas is right. We got guess one. Guess one was 0. We guessed 0. Guess number 2 became -1 when guess 1 became 0. R2 became only 1. R1 became 3. D became 2 minus 3, which is minus 0.5, like this. With Z1 equals G3. Guess 3 is minus 0.5. The calculations. So guess 3 now we got it to be this one. This is the guess that's going to work. Once you have 2, then you just get the average of those. The calculations are we know that y1 is 1. Z1 is minus 0.5. Okay, we got that Z1 is minus 0.5. And then y2 is 1 minus 0.5. 0.5. Z2 is minus 0.5. Okay, we're using Euler here. And obviously we know that the slope is 1 into the slope of Z, like Z primed is y plus x. So it's going to be y1, 1 and x1. And this is 1.5. Y3. 0.5. 1.5. So y3 is going to be y2, which is 0.5, plus the slope times y primed of 2. Right, and y primed of 2 is right. It's y primed of 2 is z. Right, so it's gonna be z of 2, which is 1.5. Good. Right, so the sum here is 2. Okay, and this is what we want. So we got now y3 equals 2, which is what we expected. We see that the third gas leads us, and most importantly, leads to the correct value. To the correct value of y of 3. Okay. Okay, let's give a note. Let's just give a note. Right. The differential equation here is linear. So we know that only one interpolation is needed for a nonlinear equation. We might need to keep interpolating and making new guesses until Y3. Until Y3 is within a given tolerance. Of the correct value 2. The approximate solution to the boundary value problem is therefore Y1 Y2 Y3. Right, so the approximate solution to the boundary value problem is therefore Y1 equals 1, Y2 equals 0.5, and Y8 3 equals 2. Right, so we have discussed this here, and we'll continue tomorrow. Okay, right, we'll continue tomorrow.